Today we're going to be talking about a lumped electrothermal model for a battery module with a novel hybrid cooling system. So, oh, jumping straight into it, the current model for our system has seen some major changes from the previous versions. Uh, Time temperature model has been developed, and we have implemented the heat transfer models from the previous versions. The resulting simulation now provides us with the thermal behavior of all battery cells within a module over a specified period of time. The graphs to the right will show us the results from our simulation with the next to the results from the research paper. As you can see, our simulation resembles what was found in the paper, uh, but with some slight deviations in the temperature ranges and the differences between the cell temperatures are not as drastic in our simulation. Below that, we have the data from the previous models, and as you can see, we have since fixed the incongruencies in the conduction heat transfer rates. In other words, the two models now seem to agree with each other. Moving forward, we will try and reduce the error in our results and the research between, or the error between our results and that was found in the research paper.
Okay, this week for the ANSYS simulation, I focused on the heat generated by the battery cells. And so I did that by modeling the charge-discharge cycle of a single battery cell. I was still having difficulties with the 12-pack battery cell. So I simplified it down to a single one and focused on that charge-discharge cycle. So I made a couple assumptions. I had assumed a C rate of 0.3, which just means it took 3 hours to discharge, instead of a charge rate or a C rate of 2. I did an initial state of charge of 0.5. I didn't see initial state of charge mentioned in the report, so I just went with the assumption of 0.5 because I was following a tutorial, so I just made some similar assumptions in order to make sure I could get a simulation working. I also assumed a reference capacity of 10.5 amp hours and material types of aluminum for the active cell and copper for the positive and negative tabs of the battery, as well as the heat transfer coefficient of 5 watts per meter squared Kelvin on the walls. The top figure, that's the charge-discharge cycle for 50 time steps. The black lines are going to be the overall energy charge. The green is the negative charge, and then the red is the positive charge. And then the bottom is the temperature contour, again, with just the energy being generated by the battery. So nothing with the flow channels or the active passive cooling. And the blue is the cooler regions, the red is the warmer regions, but there was very little temperature variation between the two. As I believe it was only 300 Kelvin was assumed. I did not see a change based off of the C rates or the initial state of charge, but I will play around with that some more. Probably have to fix some boundary conditions. And so overall, this did not align with the results of the paper yet, as there should be at least a temperature change of about 3 degrees Celsius over a total time of 1,000 seconds. Okay,
Moving forward, we have the financial breakdown. The first thing I worked on was the startup analysis. I looked at 5 key objectives, first being the articles of registration filing fee. In California for 2023, this fee is actually waived for all businesses. Second is business entity. This comes out at around $70. Third is business and website domain, which is an annual fee of $15. The fourth one is the statement of information fee. So LLCs, since we will be moving forward as a company as an LLC, this costs $20 using the LLC-12 form. Lastly, we're different annual costs. So $800 annually if revenue for that year is under $250,000. If it's over this amount, the annual tax will increase. Moving on to the next slide, we have the market analysis. So California is actually the leader in electric cars. So 39% of electric cars nationwide are found in California, which is very important for us because we are going to be based out of Pomona, California. There's actually a CAGR of 30.26%. This is from the Fortune Business Insights. So they're stating that the global electric vehicle charging station market is projected to reach over $100 billion by 2028. Along with that, in 2022, the number of electric vehicle chargers in California was 80,000, and throughout 2023, the number of EV charging stations will hit approximately 170,000. And lastly was the market gap. So an analysis was done by the California Energy Commission that states that California will need 1.2 million chargers by 2030 to keep up with the fueling demand. Thank you.